Hello everyone, a very good evening to all of you. Welcome to this exciting series of MI2, which stands for Machine Intelligence on Modern Infrastructure. My name is Janaki Ram. I'm going to be the presenter for the day, and I'm very excited to bring you this brand new series where we talk about the convergence of machine intelligence with modern infrastructure. Last year, I ran a series called Cube.live, which was exclusively focused on Kubernetes. And thanks for your support and encouragement. That was one of the most successful webinar series I have run so far. With that encouragement, I am now expanding the scope of Cube.live to include elements like cognitive computing, IoT, and machine learning. So what you can expect from this series is two things. One, we are going to talk to you more about the machine intelligence part, cutting the spectrum of IoT, cognitive computing, artificial intelligence, deep learning, and machine learning. At the same time, there is modern infrastructure which will continue to focus on Kubernetes, but with an expanded scope of service mesh, monitoring, serverless computing, microservices, and more. So the goal is to bring you two cutting-edge technologies, two different tracks, one from the machine intelligence, the other from the modern infrastructure. And today's session is focused on the machine intelligence part, which is essentially the Azure ML platform. So this webinar series is going to be a bi-weekly series where we are going to bring you one session every other week. So today's session is going to be focused on machine intelligence. The next session will be focused on modern infrastructure. You can sign up for the upcoming webinars and take a look at the calendar at mi2.live. So without further ado, let me get started. But before that, I want to bring up a quick poll to just get a sense of how confident you are with machine learning and what's your experience. So you're going to see a poll on your screen. Take a few seconds to respond to that. So how do you rate your ML skills? All right. So looks like most of you never used and some of you are novice users, which is absolutely fine. The goal of this presentation is not to really overwhelm you with a lot of concepts, but to walk you through the big picture of machine learning platform as a service and how Azure plays a crucial role in that. So for those of you who actually voted yourself as an expert and with intermediate skills, I have another poll based on the platforms that you have used. So those of you who consider yourself as intermediate to advanced users, please tell us which platform you have been using. So there is Amazon SageMaker, Azure ML, Google Cloud ML Engine, IBM Watson, or other. All right. So majority of you are using Azure, though Azure ML service is new. Azure ML as a platform, as a combination of tools has been around for a while. So looks like many of you are familiar with Azure ML Studio and other components. Excellent. Thanks for letting us know. This would really help me streamline the content and making sure that it aligns with your expectations. All right. So let's get started. What are the objectives for this session? So I'm going to talk to you about the life cycle of a machine learning model. And this is going to familiarize those of you who are not very familiar or don't consider yourself as an advanced user of machine learning. So I'm going to walk you through the elements of ML, and then we'll take a closer look at the Azure Machine Learning Service. This is fairly new. This was announced at Ignite in September, and it became generally available a couple of months ago, actually in December last month at Microsoft Connect. So I'm going to give you the big picture of Azure ML, and like most of my sessions, it is going to be completely driven through a demo. So very few slides and more of a demo. And the good news is the entire code configuration and the Jupyter notebook is available on GitHub. So I'm going to leave the link with you. And also this article is going to be made available at the Newsstack. So you can sign up for the Newsstack newsletter and the RSS feed to get an update on the complete tutorial based on this session. All right. So let's understand a little bit about what it takes to build a machine learning model. So machine learning models consists of two elements at a high level. The first one is data, and the second one is a proven statistical or a mathematical model. So when you combine the mathematical model with an existing data set, you get predictive models or predictive algorithms that can precisely tell you what can be the outcome based on the existing data. So machine learning is a combination of these two. Lots and lots of data, which we call that as a historical data, and one of the hand-picked algorithms that's going to help us perform some analytical insights on existing data. But before we actually get to do that, we need to go through a few steps. So once we have historical data, we need to split that into what is called as a training data set and the test data set. Sometimes it is 50%, sometimes it is 75% and 25% split. But it's ideally a good idea to separate them into a test data set and a training data set. And then the training data set is fed to the algorithm, which is going to evolve some kind of a model, which is going to help us predict from unseen and unknown data. So if we feed this data to the algorithm, we are going to get some outcome. For example, we feed the rainfall from a specific region for the last 100 years, and now we want to predict the rainfall of the upcoming season. So once we take the training data set and feed it to the algorithm, we have to train it. So basically, we have to go through multiple iterations to make sure that there is some prediction that is going to come out. And the algorithm does give us some prediction. But how do we know it is accurate or not? So what we do is we take this algorithm and apply it to the test data set. And since the test data set already has known values, we compare and contrast what is coming from the algorithm with the outcome already there in the test data set. And we go back and tune the algorithm till the outcome that is coming from the algorithm is very close to the actual values that are already available in the test data set. So if we have 100 years of rainfall data, let's say we feed 75% of that is 75 years of rainfall information to the algorithm, and the outcome is tested with the 25% hidden data that is stored in the test data set. And this process is very iterative, and we freeze the model only when we actually get to see the accuracy. And once the parameters are frozen and the algorithm is frozen, we evolve a final predictive model to which we are going to feed unknown, unseen live data, and the model will come out with a prediction. So at a very high level, I know this is oversimplification, but this is how machine learning is done. It doesn't matter whether you are doing logistic regression or linear regression, or even sometimes deep learning or neural networks. These are the fundamental steps involved in performing machine learning at scale. So if this is the pipeline that we're going to deal with, what are the other elements involved in it? Well, this is one perspective of looking at the life cycle of a machine learning model. But before we perform this, we need to have the test bed in place. We need to have the entire environment in place. And then the prediction is going to be accessing a frozen, a fully trained model, and there could be million requests hitting that predictive model. Is that ready to scale, right? Those are the questions that come up once we start moving and productionizing or operationalizing the trained ML models. So when it comes to real enterprise operational ML training, there are multiple things. At a high level, there are three teams that are going to get involved. Definitely, there is a DevOps team, which is responsible for provisioning and configuring the entire environment. Then there are developers and data scientists who work very closely in training and tuning. And this is the iterative process where we take an algorithm, apply the trained data, get the outcome, compare it with the test data, and keep tuning it. So this is where the developers and data scientists will collaborate. And once the model is evolved, it again gets handed over to the DevOps team and the deployment takes place. And once the deployment takes place, it got to scale. And this is a very iterative process. Every time there is a new version of the ML model that comes out as a part of retraining, it got to be pushed as a new version into production. it got to be deployed, it got to be scaled, it got to be monitored, and it is exactly like any other production web application or mobile application. So there are multiple teams involved in making this happen. There is DevOps, whose responsibility is to provision, configure, deploy, and scale. Then the developers and data scientists who will work on training and tuning. So data scientists are responsible for picking up the right algorithm, right statistical model, while developers are using Python frameworks and toolkits to basically bring these mathematical models and applying them to the data. So this is how the life cycle typically happens. But the challenge is developers and data scientists are not familiar with provisioning and configuring and deploying and scaling. So they rely on an external team for performing these steps. But the evolution of public cloud has started to blur the line between these gray boxes that we are seeing, like how Heroku and IngeneYard, or even Google App Engine or Azure, have made it very easy for developers to bring their code and scale it in the cloud. Machine learning PaaS is the latest cloud service delivery model, which is blurring the line between DevOps, developers, and data scientists. Now, developers or data scientists can directly take control of all the phases without relying on DevOps for provisioning and configuring or deploying and scaling. And that environment where developers or data scientists can take control of this entire workflow and entire pipeline is actually called as a machine learning platform as a service. So why does this become important, and what problem does it solve? Well, the good news about machine learning is everything is open source, right? From Python virtual machine and Python runtime to toolkits like NumPy, scikit-learn, Pandas, all of them are open sourced. And even deep learning frameworks and toolkits like TensorFlow, PyTorch, MXNet, Microsoft CNTK, all of them are also open source. And then the drivers that actually connect the higher level frameworks to the underlying infrastructure like GPUs, and I'm talking about NVIDIA, a Tesla K80 or P100 GPUs, or Google's TPU, or Microsoft's FPGA. You have open source software for most of them to connect your higher level programming to the low level graphics processing units, which is GPU. That is also mostly open source. But the problem is the mix and match of these layers is becoming a nightmare. For example, certain versions of TensorFlow will not work with certain versions of CUDA, which is the programmable interface exposed by NVIDIA. And similarly, certain version of scikit-learn may not work with a specific version of Pandas. So it is becoming a very, very complex matrix to deal with. You got to make sure that your environment is thoroughly set up with all the compatible layers in place, and it is exactly applicable to your requirement. And getting this combination is very, very complex and sometimes overwhelming. So DevOps teams create Terraform templates, CloudFormation templates, or they create a lot of scripts to basically spin up an environment that has all the layers, all the compatible environments asked by the data science team. But doing this very often is very painful. And even though there is automation, it is still pretty complex, pretty cumbersome, and requires a lot of handoff between one team and the other. Now, enter ML PaaS. What it basically does is it takes away the friction involved in setting up these environments that are using a permutation and combination of frameworks, toolkits, and drivers. So it just makes it very easy for a data science team to spin up a GPU or a CPU based training infrastructure, and then take the trained model and deploy it in a environment like Kubernetes or a GPU based inference environment without ever asking the DevOps team, which means they have APIs and tools that they can directly deal with. So ML PaaS is exactly like a developer PaaS, right? In developer PaaS, if you are familiar with Cloud Foundry or OpenShift, you basically take your code and then you create a config file that tells, take my code and run it with this configuration, and you submit the config plus code to the PaaS, and the PaaS will magically provision and scale your application. Now, with ML PaaS, it's exactly the same. The data scientist or developer will bring three things. He'll bring data, he'll bring code, and he'll bring an environment configuration. And the ML PaaS will take all the three and builds the entire pipeline for them to go from 0 to 60 in no time. So that is the beauty of an ML PaaS. And there are quite a few ML platform as a service offerings available in the cloud. Azure ML is one of the most recent incarnations, but Google Cloud ML Engine has been around for a while. Then Amazon SageMaker has been getting a lot of traction. IBM Watson Studio is another machine learning PaaS. And then there are other players who are fairly new, like Paperspace. Then there is Floyd Hub, and there is one more called Cluster One. There are about a dozen ML PaaS platforms that are getting a lot of attention. And today's focus is Azure ML. So what exactly is Azure ML? Well, if you are familiar with Microsoft Azure's AI strategy, you know that Microsoft is one of the leaders when it comes to delivering on all the layers of AI and ML. It has cognitive services, which will give you API access to NLP, computer vision, translation, knowledge, and so on. So it is just one API away. You can do object detection to language processing, translation, whatnot. You don't need to be an ML scientist or a developer to access those. That's a cognitive services. Then we have ML Studio, which will give you an IDE-like environment within the browser. You can drag and drop, you can connect the dots, hit a button, and then the training kicks off and everything comes out as inference. That is ML Studio. But the most recent edition is the ML PaaS, which will give you best of both worlds, which is control and flexibility. You can precisely control what environment you need. For example, you can ask ML PaaS to create an environment with TensorFlow, CUDA, NumPy, and Pandas. And at the same time, you can also choose what kind of a compute structure you want. For example, you want it on GPUs or CPUs or local compute. You can basically choose the target environment where the training kicks off. And then you can also log all the metrics and parameters that come out as a part of the itinerary process of training and tuning. And then finally, when it comes to deployment and scaling, you can target Azure Kubernetes Service or Azure container instances or plain vanilla VM clusters to basically take your model and serve it at scale. And all of this can be done via the portal, which is the Azure portal interactively. You can automate it via CLI, or you can also call it from your API using Python SDK. The beauty of Python SDK is it integrates pretty well with IDEs like Jupyter Notebooks, PyCharm, or VS Code. So a developer or a data scientist can call one line of code to do any of these steps in the workflow. It is a very comprehensive, very robust environment that addresses all the issues involved in creating very iterative, very complex machine learning jobs. So what exactly is Azure ML? First thing, it is a managed service to build, train, and deploy ML models. Now, when I say managed, what it means is you will never have to monitor the uptime or worry about the availability of the platform. This is very different from a DIY cluster that you're running by spinning up a DSVM or a DLAMI on AWS. This is a Microsoft managed service, which means they will give you SLA baked environment with very assured uptime and high availability. It integrates very well with Python environments, frameworks, and tools. It doesn't restrict you on what you need to use or a set of frameworks. You're free to use anything as long as that is Python 3.x. The APIs pretty much cover everything end to end, which means you need not even leave Jupyter Notebook or PyCharm environment when you're kicking off a training job and taking it all the way to the deployment and scaling phase of the life cycle. You can mix and match on-prem, cloud, and edge environments. What it means is you can basically test the training on your local Mac or Windows or a Linux box, or you can train it at scale using very powerful GPU infrastructure. And when it comes to deployment, you can target cloud, or you can even target a Raspberry Pi, which is running Azure IoT Edge environment. So it is a pretty comprehensive compute target, all the way from VMs to Kubernetes pods to containers that can be deployed to edge devices. It's very tightly integrated with Azure Security, Compliance, and Virtual Network, which means you can mix and match a lot of existing Azure best practices when it comes to training and deploying your ML models. And one of the key differentiators when compared to other environments is AutoML. So AutoML reduces the effort and the complexity it takes to iterate over multiple times to evolve the right model. For example, with AutoML, you need not even choose a specific algorithm. You can let the platform decide which algorithm is best suited for your problem. Second thing is feature engineering. AutoML does feature engineering pretty well. It's not your responsibility. The third one is hyperparameter tuning, or tuning the actual parameters it takes to evolve the right model. AutoML does that very effectively. And the best thing is it is not meant only for deep learning. You can also do it for classic machine learning, dealing with basic regression and logistic and classification. So it is one of the unique features when it comes to Azure ML. It includes experiment tracking, which means for every iteration, you can log certain parameters and metrics and you can play them back. So you're not really lost in time when it comes to running multiple versions and multiple iterations of your model. There is model management, which means every time you evolve a model, you can register with a repository and you can assess the effectiveness of each model. And you can also integrate this with existing CI/CD models coming with Jenkins or Spinnaker or Azure DevOps. And you can effectively build a very integrated pipeline between machine learning and your rapid software delivery CI/CD pipelines. All of that is possible with Azure ML. So those are the features. Now, when it comes to the bigger picture, basically there are these phases which aligns with our machine learning lifecycle that we have talked about. So you prepare the data using a third-party service or your Jupyter Notebook. For example, you might want to prepare your data using Azure Databricks, which will give you a Spark cluster and a pretty scalable environment for preparing the data. Or if you want, you can also deal with pandas all by yourself. But once the data prep is done, you basically experiment, which is training and testing your model. And once that is done, you register and manage your model. And that is the deployment phase, where you take a fully trained model, package that as a Docker container, and then you deploy it as a web service that is available as a REST endpoint. And in my demo today, I'm going to show you all these steps in half an hour. So the promise is we'll walk you through all these steps, all the way from data prep to exposing that as a web service and invoking it from command line to basically perform predictions. So Azure ML service does all of this very efficiently. So taking another perspective and looking at Azure ML from a different dimension, there are two environments. The first one is a training environment. So you take your existing data, you take a Python script, and then you can decide where you're going to run the training. So there are multiple choices of compute. For example, you can do it on your local machine. If the data set is small and your algorithm is not too complex, you can pretty much run it on your local CPU-based machine, which could be your Mac, Linux, or Windows, anything that runs Conda or Anaconda. Then you have a choice to run it on a remote computer. For example, you have your data center and you have an NVIDIA-based bare metal cluster running GPUs. So you can actually run your training job in your own data center running CPU or GPU. That is the second choice. The third one is Microsoft provided VM cluster. So here you are actually tapping into the managed training cluster provided by Microsoft. And the third option can be again based on CPUs or GPUs. And all of this is very transparent. One line of code can target either local or remote or the cloud for the training job. And once you hook your Python script to a compute target, then you can start logging the parameters and capturing all the parameters that are actually coming out of your training job. So that is going to be logged into Azure environment, so you can track them. And once the experimentation is done, and experimentation is basically the iterative step-by-step process to evolve the model, you have frozen your model, and then we move into the deployment phase. So here we take the fully trained model, and by the way, a fully trained model is not like a magical black box. It is essentially a job lib file or a pickle file. Currently, Azure ML recommends that you use a pickle file. So we take the pickle file and we wrap it around a Docker container image. Again, you need not do that. It is one call away. So when you publish the model, the next step is to turn that into an image. So Azure ML will take your model, will create a Docker file out of it, and creates a Docker image. And once a Docker image is created, you can target a deployment environment, which can be AKS, which is Microsoft's managed Kubernetes cluster, or you can target ACI, which is a cheaper option, but not very scalable. That is Azure Container Instances, a serverless container platform. The third one is Azure IoT Edge. So you can target any of them and then again call one API, one method, and the final outcome of that is a web service endpoint or an IoT module deployed in your edge environment. So this is pretty comprehensive. And the best thing that I love about Azure ML is all of this is done from code. You don't need to switch back and forth between a CLI or a GUI or Python API. If you spin up your entire environment and you have a Jupyter notebook, it just takes 10 minutes for you to use all those steps and you're totally in control. Don't get overwhelmed by this slide. This is the complete hierarchy and the big picture of Azure ML. So if you focus on a few things, for example, when it comes to experiment run and then output. So if you actually look at output, it can go to the Azure Container Storage or Azure Application Insights. Sorry, those are the resources, but the output files can be stored in Azure Storage if you want, or it can just get into the Azure experimentation repository. And similarly, when it comes to deployments, the extreme right side of your screen, you can target IoT Edge or web services, and web services can also capture service telemetry and model telemetry that can be visualized via Azure App Insights. So this is a pretty comprehensive one. And similarly, when it comes to compute targets, you can target a variety of environments for training, as I said, local, cloud, a remote cluster, or even Azure Databricks if you are involving a pipeline for data prep. So it's a very comprehensive spectrum, all the way from your local dev machine to a very powerful GPU-based cluster running in the cloud. So it all starts with the creation of what is called as an Azure ML Workspace. And what exactly is a workspace? Well, a workspace is a boundary for your ML project. So all the artifacts, all the assets, all the resources that are going to be created as a part of your project will be confined to a workspace. And it all starts by creating a workspace. And the workspace contains the most essential building blocks. First thing, it's going to contain a registry. And this registry is responsible for holding your Docker images, because your model is going to be packaged as a Docker image. So this is going to contain all the model images that are packaged by your experiment, and that is going to be a part of the registry. Storage account. This is very essential because when you upload data, it is going to sit in the storage account before it gets pulled by your target compute environment. Your massive data set will be first uploaded to an Azure Blob storage, and from there it gets downloaded to each of the local compute environments or the cloud-based compute environments. Key vault to protect all the access keys and passwords and usernames and so on. It is the key vault to store all the secrets in a very protected, secure form. Application Insights, again, it is responsible for tracking all the metrics that are coming from your training and deployment. So this is the core. These are the core building blocks of the Azure ML Workspace. So now, before I get into the demo, I want to give you a sense of what we're going to build, because this might get slightly overwhelming if you don't focus on each of those steps. So let me set the stage. First of all, I'm not going to build a super complicated ML model. I'm going to build a very simple, very easy to understand ML model. And this is about taking the number of years of experience and predicting the salary for that experience. And this is based on real data coming from Stack Overflow salary calculator. I have written quite a lot about that. You can go back and look at the new Stack series where I have dissected this data set and talked about how linear regression works with that as a reference example. So I'm going to take the same thing. The beauty of that is it just has one feature and one label. So we have experience as X, which is the feature, and salary as the label, which is Y. So I'm going to take that and then train that model locally because I only have X number of rows. I'm not going to make it very complex by running it in the cloud with GPUs. I don't really need to do that. So I'm going to run it on my local machine. And as we run it, I'm going to log the metrics. For example, how long does it take to train this model? What are the metrics like the slope and intercept? And what is the mean square error coming out of this experiment? I'm going to log all of them to Azure ML experiment service. And then once the model is fully trained, I'm going to register it with Azure ML. And once it is registered, we're going to turn that into a container image. And once the container image is ready, we're going to launch that image as a web service hosted on Azure Container Instance. I can choose the AKS or HD Insight or any of the other compute. I don't think HD Insight is supported for deployment, but I can pretty much target AKS for that. So instead, I'm going to choose ACI because it is just faster. So those are the steps involved. Let's get started. By the way, right after this, you should be able to access the entire code and configuration as a Jupyter notebook from this location, github.com/janakiram Azure ML tutorial. This is live. You can access it right away. All right. So let me show you how the actual model looks like. So I have a local environment. Let me show you my train code. So this is how I'm actually performing the training. Before that, let me also show you how the data structure looks like. This is very, very simple. I have 20 rows here, and the first column, which I call as X, represents the years of experience. Y represents the salary. And we only have a very tiny data set here, just with 20 rows. So the goal is if I feed in 21 or 22, we need to predict what is the salary. So I take this data and I write a simple scikit-learn application where I'm using pandas to read the CSV file. Then we are going to split this data into 75-25 split. And then I'm calling the linear regression model, fitting that, printing the intercept and slope. Basically, the intercept is, where does it start? What is the baseline salary? And slope is what is the factor by which it is incremented? And then I'm also going to perform some kind of an evaluation by checking the mean squared error. Mean squared error is if I predict how far or how close is it with the actual prediction. It's going to give us a relative number, and that number should be slightly less, or it's very relative, but this factor is going to decide how efficient or accurate our prediction model is. And finally, I'm going to export this as a pickle file. A pickle file is nothing but a serialized file of our fully trained model. And then I'm going to dump it as a local file. So very, very simple, 25 lines of code, load the data set, split it, train it, test it, and then dump it, right? So those are the steps. Now let's go ahead and run this locally. So I'm going to run Python train.py, and this is going to show us a few things, right? So intercept, as I said, intercept is the starting salary. That means for the 0 years experience, the baseline that anyone would get paid at Stack Overflow, a developer, is about 103K. Now, with every year in increase of experience, the rough increase is $1,840, right? The mean square error is $3,000. So that means if our prediction is 1,300, the actual salary is 1,000. So as we increase the scale, for example, for $100,000, $3,000 here and there doesn't make a huge difference. So an MSc of 3,000 is pretty good to measure the accuracy. That means the salary predicted versus the actual salary is plus or minus 3,000. That's what this metric tells us, which is pretty cool. So this is not way off. It is still within the acceptable limit. So this is the trained model, locally. As we see, this is like pretty straightforward. Now our goal is to take this workflow and run it in Azure ML and take it all the way from training till model serving. So model serving is exposing that as a web service and invoking it from our local machine. All right, so let's get started with that. So before we really go ahead with Azure ML training, you need to do some plumbing, very basic stuff. So you need to install Miniconda or Anaconda. That is the basic requirement. And once you have Anaconda installed, create a new environment. Let's call it AML, Azure ML, with the environment parameter, which is Python 3.6. And then once we activate the environment, we are going to install what components we need. So So at this point, we only need the notebooks, NumPy, Pandas, and scikit-learn. So we install those packages. And then because we're going to deal with Azure, so we're also going to install Azure ML SDK. And once we have all of that, we go ahead and launch a Jupyter notebook. So these are the steps involved. By the way, all of this is documented in the tutorial that's coming up at the news stack tomorrow. And this is available on GitHub as well. So you can replicate the entire setup on your machine pretty easily. All right. So now I've already gone ahead and launched Jupyter Notebook. This is already running in our environment. So here it is. So this is my Jupyter Notebook environment. And here we have our entire salary data set and training. So now we are all set to get started. So essentially there are 3 steps, right? One is, first of all, setting up the environment, right? The second one is training and testing. The third one is scaling and deploying, deploying and scaling. It's the other way. So it all starts with importing the standard Python modules. And I split them into 2 parts. One is what you need for the baseline model. And this is all about NumPy, Pandas, and scikit-learn. Nothing special, nothing great. This is fundamental to our Stack Overflow salary model. And then we need to import a bunch of Azure ML modules. So this is import workspace, very, very important. Then model, experiment, web service, container image, and then ACI web service. So we need to import all of them. And once we have that in place, we can check the Azure ML version. So currently I'm using the most recent one, which is 1.0.6. So once we have the environment in place, we need to go ahead and create the workspace. So what exactly is a workspace? Remember, the workspace is the boundary for our project. So it is going to result in the creation of 4 assets: a container registry, a storage account, the key vault, followed by an application insight. So let's go ahead and run this. While this is running, it's going to take a little while. So I have already created a parallel workspace. So let's take a closer look at it. So this workspace, as you see, has the 4 elements that are very essential, right? So this is the workspace, which is a part of the resource group. And this workspace technically contains the storage, the registry, the container registry responsible for holding all the Docker images. Then it has the app insights account. Then it has the key vault, and then the storage, right? So the container instance that you see here is towards the end. For now, with the code that we just ran, we only end up creating these 4 resources within this resource group. So this is going to take a little while, maybe a few minutes. So let's go ahead with the next step. So then once we call write config, this is going to result in saving the configuration locally. So it's going to create a directory called AML config, and it will dump a JSON file with the actual configuration. So you can always refer to that when you want to instantiate the workspace. So this is like serializing the workspace into a local JSON file. And once we have the workspace set up, then we need to create the experiment object in Python, and let's call this as salary experiment. So an experiment is like a boundary for storing all the metrics and parameters. So I'm just waiting for this to finish. Right. So here, let me move to the other one, which is already cached. So this is the experiment, right? So when we actually run the experiment, it creates the object, and then we can start logging the metrics. So here, when I actually run start logging, I'm logging the experiment time. So it's a good metric to monitor. But in deep learning, we are going to use things like the hyperparameters, the number of nodes, and a lot of other parameters that are very specific to deep learning. But since we are using a pretty trivial model, which is a sklearn with a couple of columns, it doesn't really matter so much. But nonetheless, I want to show you what it really takes to log. Then I'm going to read the data set, from data/sal.csv. We read that, and now we are in the second phase where we're actually testing and training the model. So now we are splitting the data, we are training the model, right? And then we are dumping the model into a local pickle file, and we can test the model. For example, what is the salary of a 22-year-old experienced guy, right? So this is the salary, 143K, not bad. We can also try with a couple of other parameters. So if you're 25 years experienced, you'll get about 150K, not bad. So that is basically the model that is in action, which means we have successfully serialized and we are able to test it. Now we can actually log the end of the experiment. So now I'm logging some of the parameters like intercept, the starting point of the prediction, and the slope, the increment by which the prediction changes. So we log that, and then we end the experiment because we are done with the so-called training and the tuning process. Remember, this is very trivial. And you can also get the URL for accessing all the metrics. So once I click this, you will notice that the browser takes us to the Azure portal where we can look at all the metrics that we have logged. And this is very important when you are working in a collaborative, iterative process, because you never know which iteration of your experimentation gave us the most optimal results. So this is going to give us visibility into what went into experimentation. All right. So here we go. So it actually shows us, the intercept and slope values and everything that we logged. So these are the track metrics. The experiment started and the experiment ended. And every time I publish the intercept and slope, it will come here, and you can actually see it's a visual graph. So it's a pretty cool way of visualizing your iterations and experimentation interactively within the portal. And this is the second stage, where we have now trained the model. Now we are entering the third phase where we need to register the model. So once we register the model, what it basically does is it takes the local pickle file. If you notice, this API takes the local pickle file, adds a name to it, a version to it, and register with Azure environment. So once we hit the models tab here, we'll see there are two models. The previous one that I ran during the dry run, and now this is the most recent one, SAL model version 2. So this is a registered model, which means every time we successfully freeze a model, we register with the Azure ML pass, and it shows up here. All right. So once that is in place, we need to now package that into a Docker image. But just the pickle file doesn't help us much. We need to go beyond a pickle file. So what we'll now do is we'll actually tell Azure that take our model and eventually run it in Azure container instance, which is a 1 container per VM model. So we're going to define that. And then we need to tell Azure ML what to do with our model, right? So our model will now need two things. One, the runtime environment, because when the model is serialized, the web service has to figure out what's inside that. So it needs to know that, okay, we need NumPy, we need scikit-learn, and we have some dependencies there. So we need to explain that dependency, and then we also need to tell how to really score our training model. So here we are creating a scoring model and also sending that to the Docker image. For example, here in our example, we are creating a file called score.py, and we are saying pick up the SAL model, the most recent one, and then you deserialize that, and every time there is a input data, you simply send whatever is the prediction. So you load the model here, right, global model, and when the new data comes as raw data, we are passing on that data to model.predict. We are capturing the prediction in y hat, and we are returning the JSON equivalent of that as an output of this function. And this is going to be expected by Azure ML Web Service. So we are basically feeding that information to Azure ML Web Service saying, this is the configuration information, and this is how you are going to score my model. And now take the model, the environment file, and the scoring file, and turn that into a Docker image. So basically, when we run these steps, let me go ahead and run them. So when we run these steps, what will happen is, look at this moniker, write file score.py. This will return two files, right? So when we go to Azure directory, there is environment.yaml, sal.yaml, and then there is core.py. We are basically generating these two files from the code within the Jupyter notebook. Now, what actually happens is, now Azure ML has everything that it needs. It notes that the model is available as sal_model. This is the runtime environment. The dependency is Python 3.6.2. It needs to get all the Azure ML defaults. It needs scikit-learn. And then this is how we are going to score the model. So instead of you writing a Django or a Flask web service, you are basically giving the scoring.py to Azure ML saying that take all these three and turn that into a Docker image. Now we are going to take this and turn that into a Docker image. Now this is going to take a little while. So once I run this, what happens is when we go to the portal and click on images, we'll actually notice that the previous step has created an image, right? So this image is nothing but a Docker image. And this Docker image is now containing everything that we have fed. It has the actual serialized model. It has the environment so that it can be installed with all the dependencies. And then there is core.py. By the way, you can also pull this image locally and run it locally. With all the context setup, you can actually test this Docker image locally, because this image is stored in the Azure Container Registry created as a part of your workspace. You can grab the credentials, do a Docker login, and then do a Docker pull to debug this if you have problems. So that is a pretty powerful way. All right, so once we create the image, then we finally expose it as a web service, right? This is going to be the most long running process. It's going to take anywhere from 7 to 20 minutes. So I'm not going to run this now, but the output is shown here. It basically creates the image, and then it takes the image, turns that into an ACI, and turns that ACI image into a web service. And finally, you can get the scoring URI, which is available as a part of our resource group. So if we go to our resource group, MI2 staging, which I have already cached and kept ready, so we'll actually see there is a resource within that, which is the SVC, right, which is the service, and this is nothing but an ACI instance, and this ACI instance has a public IP address, right? So now this is a full-fledged web service that is able to serve our model. So we can actually take this, right, and run this, if you want, run this from the command line. So now it's going to give us the actual NumPy array. Let's actually go ahead and test by sending the, okay, so instead of 45 years, I'm going to send 22, right? And now I'm going to get the salary expected for 22 years of experience. Let's also change this again and try it with other data points. So let's say 30 years of experience, right? We'll get back some other arbitrary number. So the beauty is, from training to hosting this, we have done all of that in just a few minutes, right? Even if I go through all these steps and wait for the synchronous step to finish, it won't take more than 25 minutes, all the way from loading the data till hosting your web service and accessing it. This is obviously not very secure because this is ACI and I haven't even protected my web service. But if you are hosting it in production, you are expected to do this with AKS and have full-blown security in place. Now, finally, if I want, I can go ahead and run WS delete, which is going to delete the workspace and clean up all the resources. Now, what is the takeaway? Well, if I am a data scientist or a developer and I don't understand DevOps, I can pretty much create a workspace with one API call, workspace.create. And I can jump all the way here. I can register the model. I can create the entire scoring file, and I can also create the image, Docker image, without ever creating a Docker file, without ever calling Docker build. I can actually create a Docker file and a Docker image. And then without ever spinning up an ACI explicitly, I'm creating an ACI resource, pushing my container inside the ACI and exposing the URL. All of that from code. Mind you, this is code. And this is infrastructure as code at its best and highly aligned and streamlined for a data scientist so that he never have to rely on a DevOps guy to actually do all of this. Without Azure ML Service API, you have to deal with multiple individuals, multiple processes, multiple silos, and you're still not in control. So what I personally like about Azure ML is the ability to do all of this from code, that too in a very Python friendly form. With just one API call, you can achieve 3 or 4 complicated steps at once. So that was the demo. As I mentioned, you can access and you can pretty much replicate the entire environment and go through all the steps in your local machine. Wait for the article to show up tomorrow at the news stack and clone the repo. All right, so that was the demo. Now let me go ahead and summarize what we have discussed so far. So Azure ML Service is a PaaS. Think of Azure ML as the Heroku equivalent, but to run ML models from training till deployment. It empowers developers and data scientists to programmatically access the lifecycle of the models, right? So it is pretty powerful. As you have seen, with one API, you can do a lot of things. Workspace is the logical boundary where you store all the artifacts and all the assets. You have wide range of compute choices for training. For example, all the way from Databricks to HD Insight to local compute to a cloud-based cluster, you can perform training in any of those environments. A comprehensive model management and experimentation, you can log pretty much every metric that you want, and you can visualize that in the portal. And finally, it is container-based deployment as a web service or as an edge module. And you can do all of that without ever leaving your IDE, which is a Jupyter Notebook or a VS Code environment. So that was the quick summary. Before I take up the Q&A, I want to bring up a couple of questions as a poll. So how relevant was the webinar content? I take your feedback very seriously. Please do share your feedback. Tell us what you felt. This is going to help us improve and better the delivery for the next upcoming webinars. All right, I only see 60% of you participating. I appreciate if everyone can take a second and click on one of the buttons there. Thank you. It's very encouraging to see. Finally, I have one poll. Promise this is the last one. This is the overall quality, which includes the audio visual experience, the content delivery style, the quality of demos, everything put together. How do you rate this? All right. So again, I only see some of you participating. Encourage all of you to tell me what you felt about the webinar. Excellent. Thank you so much. Really appreciate it. Now, I want to thank our sponsors. The MI2 webinar series is brought to you by the Newstack, which is our media partner. I absolutely love the folks at the Newstack. I work with them very closely. And for every webinar that you see on MI2, you'll have a corresponding article showing up at the Newstack. So typically, the webinar on a Thursday will have its corresponding article up and running on Friday in most of the cases. So thanks to Newstack, thanks to Foghorn. a contemporary edge computing platform from Bay Area. They are a cloud agnostic edge platform. And thanks to Portworx, a container native storage company, again from Bay Area, they help you run stateful applications on Kubernetes and Mesosphere. So finally, if you have liked this session, I encourage you to sign up for the next webinar, which is the infrastructure track. And I'm bringing you another cutting edge technology called AWS App Mesh. This was announced in December at AWS reInvent. And this service is enabling AWS EKS and Fargate customers to do service mesh like capabilities and achieve those capabilities for microservices. So I'm going to walk you through everything that you need to know about AWS App Mesh. And this is on January 31st at 9 a.m. PST or 10:30 p.m. IST. You can sign up at mi2.live. So thank you so much for attending this. We really appreciate, and keep an eye on mi2.live for the recording of this webinar and all the related links like the tutorial and the link to GitHub repo and so on. I'll see you on 31st. Have a great weekend and rest of the week ahead. Thank you.